I want you guys at your tables.
Yes.
Well, let me start this so that I can see the question.
What's in Michelle's?
I want you guys at your tables to answer the following question. I want you to write it down, and then I want you to talk about it.
Because the water's like overweight.
All right, ladies and gentlemen, bring it back. Bring it back.
Bring it
In
back.
5, 4, 3, 2, 1. I'm not going to tell you why just yet. But what I am going to do is we're going to simulate this. Okay? We're going to simulate this today. So what I have done is I have sand, and I have water, and I have 2 thermometers, and 2 identical beakers, a mass balance, okay, and a hot plate, which we're going to turn on right now, to simulate heat.
Like the sun.
But we're going to let it warm up so that it's constant. Okay? So we're going to let it get up to temperature before we use it.
How do you know what temperature it is? Like, how do you know when it's
I
ready?
turn it on until it's roughly it takes a couple of minutes, but I turn it on and let it get warm, and I'm gonna guess it's gonna take about 5 minutes for it to be totally up to temperature. All right, the first thing we need to do is we need to, okay, Mr. Shane, we need the exact same mass. Okay, why is it important to make as many things the same as possible when performing an experiment? Ms. Walker.
So that the experiment is accurate.
So the experiment is accurate, okay, and Ms. Studi?
And because in an experiment, you can only have one thing change, like one variable.
Okay, so in an experiment, we can only have one thing that is different or changing. So we want to have the same containers, the same thermometers, the same heat source. We're going to use the same mass. And the only thing we're going to do different is what?
Sand and water.
We're going to change the substance for heating. Okay? So, I'm going to go ahead and put my beaker on here. I'm going to turn it on. Now, an electric balance, ladies and gentlemen, like this one,
Is that new?
is meant to be precise. Okay? It goes a couple places past the decimal. The more decimal places you have, what happens to precision? As we increase the decimals, our precision increases. If we were to decrease the number of decimals we have, what happens to our precision?
Less and less.
It gets less and less. So this device is designed to be very precise. Very precise. So I'm going to go ahead and put my beaker on here.
Oh, so you know how much the beaker weighs before you put the sand
Right.
in?
Now, these balances have a really neat feature. There's this button here called 0. And if I hit it, it takes away the mass of the beaker. Now, is it really taking away the mass of the beaker?
No.
No, but it's eliminating it into my calculation so that I know exactly how much sand I'm putting in the beaker by mass. Okay, and we measure mass in grams. So I'm going to take my sand.
What type of sand?
Oh, it's sand.
Well, is it like beach sand or like?
Oh, it's probably got a little quartz
Lake
in
sand.
it. You know, there's different sands from all over the world. It might have some
Exactly.
potassium feldspar.
Because beach
Might
sand
have some
and lake
mica
sand feel
flakes.
Some diamond.
Okay,
Or
Okay.
some leftover
so
beer cans.
we'll just have to wait and see.
different.
All right, so I'm going to go ahead and add sand. I want more than that.
Remember when Jacob killed someone?
Moon sand at its best.
Okay.
Yeah, Jacob killed somebody on that.
On what?
No, it's Mars.
Yeah, literally Jacob
All right.
killed-
Sand from Mars.
We are measuring.
The world will end if Mr. B gets this wrong.
How much
All
do
the
you want
oil
in there?
pulls up.
I want approximately 60 grams.
How many do you have right now?
Oh yeah, I saw that.
All right,
video.
I have 61.0 grams.
You
many
just
grams
killed
are in a
6
pound?
people in a van.
You're 1 gram over.
And they
You
were
How many
just
grams
killed
are in a
someone.
pound?
You just killed someone, Mr. B.
Depends. Wait, but we're not going to get into that discussion today.
That's
That'll
bad.
be the end of the semester.
Okay.
I got a
Sounds
question.
difficult.
Okay? 61 grams. Please write that down. 61 grams of sand. Okay? Now, I'm going to take my beaker on here, and I'm going to zero it out. Okay? I'm zeroing it out. I'm going to add how many grams of water? 61. I want the same amount. And notice I use the same size beaker. Why might that be important? Okay? Caleb?
For the weight.
Okay, it could be important for the weight of the beaker. Sure. What else could be important when I put them on the hot plate? Okay, what if I had a really, really small beaker that was very, very tall? How might that be a problem for me? Isabel?
Because it would heat up faster than the other one.
Okay, it could heat up faster, but
Or slower.
well, don't go back. Just, let's say I put them on here, okay? What is in contact with the hot plate?
The glass.
The glass, but what part of the beaker?
The bottom.
The bottom. If the bottom is a lot smaller, can there be as many collisions take place?
No.
No, okay? And when I have something that's in direct contact, is that convection or conduction? That's conduction. Because of collisions between the atoms. So if I have the same size beaker, I can have roughly the same number of collisions happen. So that also eliminates any possible variables in my experiment. So again, I have my beaker, I'm going to put it on here. It's going to be zeroed out, and I've already done it. So now I'm going to start adding water, and I need 61 grams, and you guys all reminded me of that, thank you. So here we go. Okay. Oh, all right. And, oh, all right.
What's
Oh,
that?
okay, we're
Dolphin.
and, oh, all right, we're getting close. We're at 57.2,
Oh, snap.
58.3,
Snag.
59.5. Oh,
You just killed someone!
You just killed 6 people in a homeless van.
62.5. So I got to pour some back out, put it back on here. I'm at 60 exactly, okay? So I need
Now it gets.
Is this hard to do?
1 gram of water.
Don't they have robots in this though?
Okay.
What are you at?
What if you killed someone again?
Oh my gosh.
Mom, do you see that little like
Don't
droppy
kill me
thing?
over
Yeah,
fans.
use the droppy thingy.
Oh, like a pipette.
Yeah,
Or use
like what
Jackson.
you use for
That is in the back.
Or use SpongeBob.
I can go get it now.
Oh,
Gemma, sit down.
My turn.
Gemma Cyrus. Sit down.
61.
Exactly.
What if it was
61 exactly.
Oh,
Okay.
What if the water evaporates before you get
And actually, it's kind of fluctuating, so we'll put
What
just
does
a couple
that mean?
more microscopic drops to solidify it.
What does fluctuating mean?
It means it was going between 60.9 and 61. It kind of bounces back and forth. So I just added just a hair more water, and now it's staying at a solid 61. So I'm going to go ahead and take it off there. I'm done with my balance. I'm going to turn it off.
How many grams did the beaker weigh?
I'm going to just set it off to the side here.
Great hands.
Now I have my 2 beakers. Now, notice I'm going to go ahead and I have 2 thermometers that are both at room temperature. So they're starting at exactly the same temperature. And I'm going to stick them in the sand. Okay? I'm going to stick it in the sand just like that so that it's sitting in that beaker right in that little groove. And I'm going to stick this one in the same spot in the beaker so that they are almost identical
It just went
except
way
for
down.
the sand in the water.
It just went way down.
It went way down.
The water did when you put it in. I saw
Well,
that.
the temperatures are reading the same. Okay? The temperatures are reading the same. Now,
Are they in Celsius?
they're in Celsius.
The thermometer could change the weight in grams of everything.
I
You're
could
right. The
change the
thermometer
weight of it.
could change it. And that's something you should probably take into consideration. But I used the exact same type of thermometer to try to minimize any sort of outside impact they're going to have on my experiment. That's a good point. Good. All right. Now, I'm going to time this. I'm going to let them sit on the hot plate for 2 minutes. Okay? So I'm going to let them sit on the hot plate for 2 minutes. I'm going to put them both on. I'm going to try to do it exactly at the same time. Now, I'm going to get them... Now I'm going to let them have roughly the same amount of space on the hot plate. And we're going to start. Now, we're going to use these 2 minutes to kind of go over again just a few things with convection and conduction. Okay? Conduction is the heating of a substance through what?
Contact!
Contact.
Listen.
Collisions between the what?
Heat transfer through
Atoms.
collision is
The
conduction.
atoms. The atoms collide, they transfer energy.
I feel
Okay? But now, there is a thing called convection, and what we have to remember is convection is when we have this what kind of motion happening. It's like a circular motion, right? And in something near the bottom that's heating up, it does what?
Expands and flows.
It expands and floats, okay? And then it
Loses energy.
and shrinks and sinks. If you can remember that next week, you're golden.
Expands and flows.
Okay?
Shrinks, sinks.
Ah.
Expand, flow,
Sink,
sink, expand, flow, shrink, shrink.
All right.
Smells like a
I love it. I love it. All right. We are at a minute. I'm going to do this. I'm going to just slightly stir both of them a little bit so that I get an even distribution of heat.
Meow.
Okay, I'm going to just stir them a little bit.
And on YouTube,
Yeah, there's really you see people.
Okay.
I am not
All right.
technically wearing them.
Now, I'm going to tell you guys right now that we're starting to see, what do you think? Do you think they're heating? Do you think I'm seeing the same temperature, or do you think I'm
No,
seeing a
not at
different
all.
temperature?
Different.
Okay, we have 20 seconds left.
The sand is way hotter.
You think the sand is hotter?
From the way I see the things,
Okay.
the thermometers.
Well, let's do this. When it gets to 2 minutes, I'll take a picture. And I'll include it in the recorded notes or the presentation here. All right, so I want you guys to be able to see exactly what's happening here. Okay, I took a picture. Another one. All right, and we are going to take them off in 5, 4, 3, 2, 1, and off. Going to give you quick readings. Write these down. The water is at 44 degrees Celsius. The sand is at 54 degrees Celsius.
What's the same?
Okay, we're going to turn our hot plate off because we don't want it to be sitting warm. All right. What happened? Which one heated up more? Grace.
the sand.
The sand got warmer, which means that it was able to gain temperature. The particles moved faster, but, and here's where it gets tricky. Ladies and gentlemen, I put them on the same hot plate that was putting out the same energy. I'm going to tell you right here now, they absorbed probably the same or close to the same amount of energy.
Wait.
And yet, the sand is hotter. As a matter of fact, it's retaining that energy. It's actually increasing in temperature right now, whereas the water is starting to come down. So there's something about the way that it's constructed. There's something about its very nature that's different. And don't just say, well, one's sand and one's water, Mr. Bornheimer. Okay, well, that is a true statement. But there's something else at work here. And it will actually help us to describe or explain why on a hot summer day you go out on the beach, you go in the sand and you're like, oh, 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 and then you get to the water and you're like, oh. Okay? So, let's transition to the whiteboard. We've talked about temperature as being the what of the kinetic energy? What? Yes. The average measure of the kinetic energy. Average measure of the kinetic energy of the what in a substance? What is it? What is a substance made out of? Atoms, molecules, particles. The average measure of the kinetic energy of the atoms / molecules of a substance. Okay, average movement energy, so to speak. That's temperature. And we've discussed, and this is just a mini review, we've discussed that we know objects can have different amounts of total energy. We call this thermal energy. And I'm just going to draw two little pictures here to kind of emphasize this idea. If I have a very large container of water that's at, let's say, 2 degrees Celsius. I'm going to draw a container of water. It's at 2 degrees Celsius. and I have a smaller container of water.
Is this a picture we're supposed to draw?
This is going to be one of them. Okay? If I have a smaller container of water, okay, which one is going to have the most total energy? If I add up all the energy of all the atoms in that substance, which one's going to have the most total energy? What do you think? Which one has more atoms?
The bigger one.
The bigger one. So the bigger one, if I add up all the energy, is going to have more total energy. Okay? So we're going to say that this one has more total energy. Okay? So it has more thermal energy. All right? More total energy.
Stop it.
Now, case in point, Mrs. Bornheimer is much smaller than Mr. Bornheimer. Mr. Bornheimer is getting bigger by the year, unfortunately. Okay? And so, as I love that's in my recording.
David Jackson.
I'm getting bigger by the year. I am roughly 98.6 degrees Fahrenheit, or roughly 37 degrees Celsius. Mrs. Bornheimer is approximately the same temperature, but because I am more massive, okay? Literally, I am more massive, then I have more total energy. I have more total energy. But my body needs more energy because there's more of me to heat up. There's a lot more of me to heat up, okay? So that's the idea of thermal energy, that there's these substances that have total amounts of energy. They might be the same temperature, but if I were to add up all the energy of all the atoms, the one with more atoms will have more energy. Their average energy will be the same, but there will still be more total energy in the larger object. Yes, Corey?
Is that why boys are always never cold?
You could argue that that's probably why boys are never cold. Sure. Okay. Yeah. So I've just got a lot more heat to give off. Yeah. Parker.
So much better.
Okay, so it would take longer for you. So I would get mosquitoed up faster than you would if you were over a hot plate.
Not necessarily. No, I'm not going to put you over a hot plate, but no, not necessarily. Let's.
Or like if we're in the sun, I would absorb energy faster and fill myself up with energy faster than you.
Well,
Because you're so tiny.
Mr.
Okay.
B is more tan than you, so.
What you are hinting at is where I'm going with this next part of our lesson today. So keep that in mind. And if I don't answer your question at the end, we can have a great discussion on why maybe smaller people fill up faster with energy than larger people. Okay?
Is that why people that are shorter have more energy?
Okay, no. Well, we're digressing. Okay?
Yeah.
This was review. Let's talk today about something called specific heat. Okay? Specific heat. I'm going to actually write this in red so that you can take and note or notice of it.
Specific heat.
Okay. I need you, ladies and gentlemen, to write down this definition. I'm going to tell you right now that the definition may or may not make sense. Pay attention to every word
You say.
that is up here that I'm about to put on the board to describe this.
Can you write it?
Specific heat, I will. I'm going to say it as I write it. Specific heat is the amount of energy in joules, because that's the unit for energy, for every gram of a substance that increases that substance by 1 degree Celsius. Okay, I'm going to break it down for you so you can kind of get a general idea of what we're talking about here. there's other ways to word this. There's multiple ways to word the definition for specific heat. I've worded it so that we can break it into pieces. It's the amount of energy. First and foremost, we should recognize that there's energy involved here. Okay? It's the amount of energy in joules for every gram. Okay? So this is a unit for every gram of substance. Now, we had over there 61 grams of water. Okay? So I'm just going to kind of put that up here. Okay, I'm going to put that right here, 61 grams of water. We're going to come back to that. We're going to come back to that. The amount of energy in joules for every gram of a substance, like water, sand, everything, actually everything has a specific heat.
Like me.
That will increase the temperature of that 1 gram by 1 degree Celsius. Okay? Does that make sense to you?
No.
We are putting energy in to 1 gram of substance, and when we do that, when we add a certain amount of energy, it will increase that substance by 1 degree
Well,
Celsius.
that makes sense. I get it.
So let's say I am 1 gram. Actually, I am not. I am hundreds of thousands of grams. But let's say I am the representation of 1 gram. G. Okay? I'm 1 gram. I can only absorb a certain amount of energy before my temperature goes up 1 degree Celsius. If I absorb twice the amount of energy,
It goes up 2 degrees
I go up 2 degrees Celsius. If I absorb 3 times the energy, I go up 3 degrees Celsius. Okay? Now, let's just work with water for a moment. Let's work with water for a moment. Water has a specific heat. And please understand, these values have been determined. The clicking. These values have been determined in the lab. Okay? They've been determined in the lab. So,
Wait, like our lab or like a science?
in a science lab. So the specific heat of water equals 4.19 joules of energy for every gram to increase it by 1 degree Celsius. The units kind of look scary. Please understand they're not. It's just based on the definition. So it takes 4.19 joules of energy to be absorbed by every gram of water, so that then that water can increase by 1 degree Celsius. We can actually use this to determine exactly how much energy was absorbed by the water in the beaker. We can.
How many joules?
That's what we're going to do right now. So, first of all, what we need to understand is that we had 61 grams of water. So what we would do is we would multiply this number by 61. Would someone please do that for me right now?
Multiply what number?
Multiply the specific heat by 61 grams. Okay, that's going to tell us how much heat it took for every degree Celsius. Okay? Miss Pennington.
It's 255.59.
Okay, let's call it 255.6. So this is what we have found. For our 61 grams of water, it takes how much? 255.6 joules of energy to raise that beaker of water 1 degree Celsius.
So that means 255.6 times it has to like bounce back from the beaker to the hot plate.
No, not necessarily. This is what it means. You have 61 grams of water. Do you agree with that statement?
Yeah.
Okay. And for every gram of water, it has to absorb 4.19 joules of energy. That's a correct statement. So if I have 61 grams, I need that water to absorb 255.6 joules of energy to increase by 1 degree Celsius. All right, it needs to increase, you needs to absorb 255 joules of energy, roughly, to go up by 1 degree Celsius.
To raise it up.
Okay, so to raise that beaker of water 1 degree Celsius, and only 1, it had to gain 255 joules of energy, or 255.6. But did it go up by just 1 degree Celsius?
Yeah.
No.
It started at what temperature?
Room.
Room temperature. It started at, write this down, 22 degrees Celsius.
The water started at?
Yep, very good. The water started at 22 degrees Celsius. So it started at 22 degrees Celsius, and it went to what temperature? Just the water.
44.
Went to 44 degrees Celsius. How many degrees Celsius did it go up?
22.
It went up 22 degrees Celsius.
So 22 times
Mm-hmm.
200.
So it went up 22 degrees Celsius, and every degree Celsius it needed to absorb 255.6 joules of energy.
That's 550. It absorbed 5,623.2 joules of energy.
Hold on to that so I can explain the calculation. But yes, you're correct, and thank you. We're going to write that down in just a minute. So our 61 grams of water had to absorb 22 times 255 joules of energy to get to 44 degrees Celsius. And how much total was that? How much, Emma?
5,623.2 or 20.2 joules of energy.
Stop.
That's where it stops. Like that's it. That's the number. There's no.
Thank you, Emma, for that interview.
Mr. Bear.
Okay, so you multiply the 61 grams and then the 4.19 to get 250.
I did, yep. And then I looked at how many degrees Celsius it went up. It went up 22. This is the amount of energy needed to raise it 1 degree Celsius. It went up 22. I can multiply those two numbers. And when I multiply those two numbers, Mr. Behrman, I get almost 5.5 or 5,600-ish joules of energy. Okay? That's a lot. That's a lot. 5,000 joules of energy. Okay, let's see if, and I haven't tried this yet, so we're going to have to try this. Let's see if we can figure out how many calories that is. Like how many calories? Siri, how many calories is 5,623 joules of energy?
You are overweight. That's what it say.
Checking. 5,623 joules converts to about 1,344 thermochemical calories.
And also you are.
So about 1,000 calories.
Wait, what are chemical calories?
Okay?
I thought that'd be like 4 million calories.
Lucky doesn't need any more energy.
What if someone ate 4,000 calories in that? But
It's
now
a lot of energy. It's a lot of energy.
I need that.
All right.
No, you don't.
I wanted to show you guys, hold on. I wanted to show you guys that we could figure out exactly how much energy was absorbed. I am not going to make you do one of those calculations next week on your test.
Thank you.
Okay? But do you understand? Please, look here. Mr. King. Thanks. Do you understand that I can actually make that calculation? That we can figure it out? That using a value like specific heat, which we're going to work with a little bit more today, I can find how much energy was actually absorbed on that hot plate? I want you to understand it's doable and that it's actually calculable. And believe it or not, this is where, and we use this same idea to actually figure out how many calories food is. This is how McDonald's can determine how many calories are in a Big Mac. Okay? It's part of the same idea. It's part of the same concept. Okay? All right. I'm going to erase a few things here. Miss Maxon, you have a question?
Where did you get 5,623?
I multiplied 255 by 22. Because this is the amount of energy needed to raise it 1 degree Celsius. It went up 22 degrees Celsius. So I had to multiply the two numbers to get that very large number.
I think 22 degrees Celsius. It raised 22.
Because we actually took the measurement. It started at 22 and it went to 44.
But why do you raise it?
What's that?
Why do you raise it?
Because I heated it up on the hot plate.
No, I mean, how... Is that it for notes today? How did you get to 5,600?
Okay, hold on. I've explained this a couple times. I'll explain it one more time. I know that it takes 255.6 joules of energy to raise the beaker of water 1 degree Celsius. It takes, I'm going to say it out loud, pay attention. For 61 grams of water, it takes 255.6 joules. Mr. Shane, up here. It takes 255.6 joules of energy to raise the beaker of water 1 degree Celsius. If I want to raise that beaker of water 1 degree Celsius, how much energy do I need?
61 grams. Oh, 200.
Okay. Mr. Shane, if I want to raise the beaker of water 1 degree Celsius, how much energy do I need?
255.
Very good. Mr. Miller, if I want to raise the beaker of water 1 degree Celsius, how much energy do I need? Right. But did it go up only 1 degree Celsius?
Yes. No.
When I measured it over there, it went up how many degrees Celsius? 22 degrees Celsius. And because it went up 22 degrees Celsius, ladies and gentlemen, I had to multiply this by 22 because it's only good for one. And that's where the 5,623 joules of total energy came from. Reagan.
Okay, so I'll have 2 questions. What's the specific heat of sand? Like, how much does it...
That's a great question. The
Is it
specific
that much
heat of sand is like
I can figure it out.
0.5 or
How would you
0.6.
figure
That would
that
be my estimate. I don't actually know the exact specific heat of sand.
Okay, and then also... Okay, so is joules the
Hang on.
amount of energy in a cell?
Siri, what is the specific heat of sand?
You use your finger a lot, which is not.
Let me think. Okay, I found this on the web for what is the specific heat of sand.
Mr. B, I can figure it out right here. I wonder if anyone else is asking you about sand.
Well,
I'm sorry, my calculator.
here it is.
Ask how many.
It is approximately, from what this is saying, and take this with a grain of salt, which means could be wrong, could be right. It looks like it could be anywhere between 0.24 and 0.8. 0.24 and 0.8. That's just specific heat. So is that a lot less than 4.19?
Yes.
Yeah, and that's what we're going to get into next. I have about 7 more minutes of notes that I'm going to go through.
Ask how
And then you guys have library time. So,
much cars are in a Big Mac.
you can find that out.
What's really on McDonald's meat?
Wait, okay, and then also,
It's
Cardboard.
crap.
is joules the amount of energy in a calories?
Hang on. Yeah, Reagan asked the question.
Okay, so is joules like the amount of energy like in a substance? So it's like, I mean, it could be like 22 degrees Celsius, like the standard, and it has an average amount, but it's not like the actual amount. Is
Right.
that what joules is?
That's right. Joules is just energy. So how much energy is in something? Yep. And two things can have different energies even though they have the same
Yeah,
temperature.
okay.
Yes. All right. I want you to think about specific heat in a new way. Miss Pennekamp, do you know what cars use to hold gasoline?
A gas tank.
Well, gasoline is used by the engine, but what holds the gasoline?
A gas tank.
A gas tank. Every substance that God has ever made has an energy tank. Let's start with this. Okay? We are going to start with the energy tank of silver. Okay? And we're going to call this silver's energy tank. We're going to draw a picture of silver's energy tank right here. Now, silver's energy tank is only good for 1 gram of silver. Okay, only good for 1 gram. If I have 2 grams, well then I have to have 2 tanks, but we're not going to go there. We're just going to say 1 gram of silver has this tank that can hold energy. And when the tank gets full, silver will go up 1 degree Celsius. So if the tank fills up, silver increases by 1 degree Celsius. So I'm going to put a little plus 1 degree Celsius above it. It has to fill up though. If it doesn't fill up, it won't increase the full 1 degree Celsius. Okay, so we've got the energy tank. And we're going to fill her right up.
Ow, my ears.
Okay? So, let's fill the energy tank of silver up here. So we're going to go ahead and just go, we're going to fill it up. We're going to fill it up. Fill it up and fill it up and so that it's topped right off. We're going to top the tank right off. And right in the middle, I'm going to put how much energy it took to fill it. This number is different for every substance that we know of. The number for silver, okay, is, and let me look it up here real quick, is going to be 0.237 joules of energy. Okay? So, I'm going to put Bo in charge of my silver energy tank. And every time I want to fill up a tank so that I can increase it 1 degree Celsius, I have to give Bo, my energy banker, 0.237 joules of energy. So I go up to Bo and I'm like, Bo, I want to fill a tank today. Okay, he's going to tell me, Mr. Bornheimer, that's great. I love the fact that you're entrusting me with your energy currency. But what I need from you to fill up a tank is 0.237 joules of energy. So what I do, I go into my energy pocketbook and I write him a check for 0.237 joules of energy. And I give it to him. My tank fills up, tops it off, and boom shakalaka, I get my 1 degree Celsius.
Yeah, a little warmer thing.
And now I got a little bit of a warmer, cozier silver. Okay? However, if I want to go and I want to say, Mr. Behrman, I need to fill 2 tanks today. I need to get 2 degrees Celsius.
0.237 times 2.
I'm going to need to give him twice the amount of energy. So I go up and I say, all right,
Money.
Nina, I got to give him more energy. So I go in my energy pocketbook and I pull out a check and I write it for how much?
40,000.
Yeah?
0.474.
Yeah, 474. I got to give him twice as much energy. So I'm going to draw another tank here. And I'm going to fill this one up so I can get my 1 degree Celsius.
That was hard.
Okay? And this one can only hold the same amount, but now I've got 2 degrees Celsius increase. I've not increased it 1, but I've increased it 2 degrees Celsius, 1, 2. And as a result, Miss Pankamp is exactly right. I need to give them not 0.237, but 0.474. Okay? And of course, then every time I want to go up a degree Celsius, I just have to give them another 0.237, 0.237,
But doesn't a
0.237,
barrel like
etc.
gasoline cost $80?
Well, we're not going there right now. We're focused on something a little different. I'm using the same idea, okay? So, I'm going to say that I go to Mr. Behrman, and I'm going to give him enough energy to fill up 5 tanks of silver's, 5 energy tanks for silver. Okay? How many degrees Celsius do I want, or am I going to get out of the deal?
1.
Oh, hang on a minute. I'm giving him enough energy for 5 tanks. What temperature increase am I going to get in return? I'm not going to get 1. I'm giving him 5 times the amount of energy. How many degrees Celsius am I going to get out of the deal? Yeah.
5.
5 degrees Celsius. I better get 5 degrees Celsius. But we got currency exchange problems.
What do you mean? Oh, never mind. I don't
Everybody got currency exchange problem, girl.
Well, Mr. Bornheimer's a guy. So I call him Mr. Bornheimer.
Wait, we already have Mrs. Bornheimer. That joke didn't work out too well.
Why do you have my lid?
Would you have some weird my lid?
Jasmine's coloring his glasses with
I'm
pencil.
not coloring my glasses, I'm trying to fix them.
Oh, great. That's great.
Come here, little boy.
Wait, what time is library?
Yeah, it's right now, but we got to finish this. Okay? All right. So, in order to get 5 degrees Celsius for my 1 gram of silver, okay, actually, I'll just leave it right. 5 degrees Celsius for my 1 gram, I have to give Mr. Behrman not enough energy for 1 tank, but enough energy for 5 tanks. How much total energy did I have to give him to get my 5 degrees Celsius? Yeah.
1.185.
1.185 joules of energy. Oh man, I'm rolling in the temperature now. I'm rolling in my degrees Celsius. Okay? This is how specific heat works. Every time the energy tank of a substance fills up, that substance increases by a degree Celsius. However, silver's specific heat, this 0.237, it's kind of small. Okay? Water was 4.19. Ladies and gentlemen, this is what the energy tank of water looks like.
Now you're telling us the truth.
I don't have enough room. Do we have to draw that?
You should. Just make it bigger. It doesn't have to be this much bigger, but you should get the idea. This is the energy tank of water. To take 1 gram of water, and increase it by 1 degree Celsius, I have to put 4.19 joules of energy in the tank. I have to put a lot more energy in to fill this tank up. Let's say I can't. Let's say I want to take the same amount of energy I put into the 5 tanks of silver, this 1.185, and I dump that in here instead. How far is that going to get me? Yeah.
Like a little.
A little bit. About 1/4 of the way.
Oh, you're killing me.
So why?
I thought we were supposed to fill that thing up. So I filled it up.
Oh, you're not saying that.
This is only 1.185 joules of energy. Okay? It's only 1.185. All right. So, here's the whole idea.
Oh wow.
Isabella,
Yeah.
how many tanks did I fill up here?
26.
5.
Jackson, Emma, I'm asking Isabella. Isabella, how many tanks did I fill up right here?
5.
I filled up 5. And it only took me 1.185 joules of energy to do that. So it didn't take a lot of energy. It only took a little bit. And I got a 5 degree increase out of the deal.
Woo!
That's great. How far did I get in my 1 tank of water?
Like not enough.
Not even enough to fill it 1 degree Celsius.
Not even 1/2.
Not even half. So I've got less than 1 degree Celsius increase. Less than 1.
You filled it up with 5 degrees. I really hope this figures. Look, guys, all 5 right there. You fill up with 5 degrees.
This is totally separate. Think of this as totally separate. Over here's one problem. Over here's the next.
So you're just using the same.
I'm using the same energy.
Okay.
Okay? This is going to actually answer our question. I'm almost there. So, if I have the same energy, it's going to fill 5, Grace, if I have the same energy, it's going to fill 5 tanks of silver. It's not even going to fill 1 tank of water. That means the silver is going to go up 5 degrees, and the water is going to go up less than 1 degree because it has a larger tank. It's like if I go to a Marathon gas station and I say, I need $5 in gas. Okay? Okay? Now, let's say that I go to a Marathon gas station and I have a really small gas can. Well, I could probably fill that really small gas can up for $5. Now, let's say I take my massive 15-passenger van into the Marathon gas station. Okay? $5 in gas is that's gonna even be like down here in my tank. It's gonna be just enough to scrape the bottom.
Mr. B, your Canada van.
My Canada van.
Remember when gas used to be 18 cents?
Yeah, well, I don't. Wow, that's a long time ago.
Gas is a lot.
So here's my point. Which one of these examples, which one of these two, silver or water, do you think represents this or is similar to sand? Yeah, silver.
Silver.
See, silver is like sand. It only takes 5 tanks for a little bit of energy. It goes up very quickly in temperature. That's the library. Hang on. Whereas, is Mrs. Lash? Hello. I do. I'm in the middle of my lesson and I'm recording. Can I come down in just a minute? They do, but I had to hold them a little bit. All right, bye. Okay. Okay, hang on. So ladies and gentlemen, this is a lot like sand. Sand can fill up very quickly because it doesn't take a whole lot of energy to fill up, which means its temperature increases quickly. Water can absorb a lot more energy before its temperature goes up. So on a hot summer day, when you're on the beach, the sand, because it has a much smaller specific heat, will fill up very quickly with energy and get very hot very quickly. Whereas the water is going to absorb and absorb and absorb energy until just to get a little bit of a temperature increase. So the reason that a beach has hot sand and cooler water, for the same amount of energy coming from the sun, same amount of energy, is because sand has a much smaller specific heat and water has a much larger specific heat. Sand can increase in temperature for a little bit of energy. Water can increase in temperature, can only increase in temperature for a lot of energy. Okay?